Singh sir, and I was the student of Dr. Arya sir. So basically, I am belonging to the tree generated by Dr. Singh sir. He is like a banyan tree for all of us. He has worked in many areas. With these words, I would like to invite Professor Singh sir to enlighten us. And it's our pleasure. It's the fortune of all the participants joined here to listen Dr. Singh sir today. He has taken a very valuable time from his very much busy schedule. Generally, we visit IIT Delhi due to some works, and we see the sir's busyness is still at this age. So, with these words, this was very that means it is not sufficient to introduce Dr. Singh sir, but I hope so. Participants, you will enjoy the session of Dr. Singh sir. So, Singh sir, now it is up to you.
Well, good evening to all, and thank you very much, Professor Asutosh Giri. It's pleasure to be with you here on this evening. It's a interesting, like a kind of a, you can call it a, it's a my, pleasure to be with you here on this evening. It is always, it's a interesting, like a kind of a, so well, and probably it is good, like after COVID, we have gone most of the time online. So the topic which Professor Asutosh Giri asked me to speak about on microgrid, configuration, operation, and control, on which probably I think maybe a couple of dozen students are working on towards their PhD. Majority of them have completed. Some are still there. Who are working probably microgrid related to solar as well as wind, and they are working. Even some of them work in small hydro as well as the connected DG set with battery energy and many converters into. So let's go ahead. So well, this already he already talked about this. So well, typically if we talk about in India, the renewable is coming up. Typically wind and solar, and the government of India, especially Power Ministry, have put hydro also into it. Like so with the hydro, it goes more than 40% already, and typically the trend towards renewable energy increasing day by day. And why we need renewable energy? Because it does not provide the pollution, and moreover, it is every place. Some of the renewable energy sources like a solar, and of course these are with the from the conventional, but we can go directly for the solar. And of course these are the you can call it solar comes or biomass. All these renewable comes quite low pollution level, and especially now earlier we worked with the small hydro. For a long time, about probably a more than couple of decades. Then we came for the wind. Probably every generator my student have used, and probably now around 6 student have used on DFIG, which is considered one of the best generator for wind application. We'll talk about, and of course after that we start working on solar photovoltaic. So because solar, why we really gone, because it is available every place, including your rooftop. Not only at the remote place also. So, and it's giving the concept really for the you can call it the microgrid. Like, and of course, these are I've already told about like 40%. It's a little old data, so day by day it's changing. And this is something like how is really the renewable in India probably gone up, and day by day it's increasing. Now, this is important slide which I would like to discuss. You can think about when we started working around typically 2010 or so, around typically 14 years back, the price of typically of you can say solar was more than 6.5. Even Haryana put a tender in 2010, it was 18 rupee, and then suddenly it gone to probably 3 to 4 years around 6 rupee 50 paisa. But you can understand in the even less than 1 decade it reduced to 1 rupee 99 paisa, and like per kilowatt hour. And day by day it is reducing. I can tell you the panel probably 3 years back it was 33 rupee per watt. Today it is already gone to 13 rupee per watt, and I got information from leading, let's say the installer, typically a big industry or company. They say it will come probably maybe in couple of years 10 rupee per watt. So you can understand the price of this electricity through solar is going to be down. Of course, we were having a wind around the same, even little lesser than solar, and it's also gone down to typically even touch less than 3 rupee, but it fall back to. Unfortunately, we don't have a wind so much, only on coastal areas. We can't put the wind turbine in the water which European and American can put, like, because they have a calm sea and lake. Even for the wind, if you really talk about from Toronto to Niagara Falls, it's 120 kilometers, and you have a very big lake where you can have even a gigawatt generation. But we can't put anywhere in the water. I mean, probably IT Madras tried to put in sea around 100 to 200 kilowatt, and in one season is flash out. Like, so we cannot. The only coastal areas, I mean, like typically Gujarat, Maharashtra, and Tamil Nadu, these are the states which probably are having a reasonable wind. But I can tell you about wind story. I mean, we have around 10 year back also around 40 gigawatt, and today itself we have only 48 gigawatt. So, last 8 to 10 years we are able to add in wind only 8 to now again it is picking up, especially in the state like maybe Rajasthan, low coastal area and where the population density is quite small. But solar has picked up like probably last decade, like anything, and it's already now gone more than 75 gigawatt, and every day it's changing. Somebody was saying a couple of days back around 90 gigawatt. So this is a price reduction responsible for especially solar, and apart from solar, every place. That's the one of the reason. Now coming to like concept, I think throughout the world have been like a smart grid. Okay, so smart grid have a many. I mean, we are talking about in research probably more than couple of decade, around quarter century about the smart grid. That okay, what should be the smart grid like? I mean, but of course, in it's very difficult to translate really smart grid in today, which have a probably the many component with the intelligence also, and typically the many even people start working. But of course, the part which is a microgrid is also a part of the specific portion of the smart grid that's picking up. The reason being, you can have a small typically distribution feeder microgrid with you might have a like a generator also like a local generator, typically solar, maybe a small wind. Apart from that, you may have a DG set or you might have a CNG generator set. So it means you have a distribution renewable also, and you have a typically energy storage. I mean, different kind of energy storage, and then you have a energy consumers like load, including that the why it is coming up because the federal government wants to bring electric vehicle probably next decade, probably to convert. They plan it by 2030. They should have all vehicles electric, but that will, it's not practically possible to do that. Like I mean, but of course, day by day, I mean, if we talk about in Delhi, we have a lot of buses and now a lot of taxis, especially which have come on the road, and two-wheeler and three-wheelers, of course, are two-wheeler are coming big way. I mean, probably number I was probably talking about 6 year back that three-wheeler will come more because it's a vehicle for employment, like you can call it a kind of commercial typically item because I mean somebody have a three-wheel like e-rickshaw or the loader, he get employment through it like. But in last few years, the two-wheeler have come big way, including I mean somebody manufacturing in Gurgaon, the two-wheelers, electric two-wheelers in hardly 22,000 rupee, and all the food vendors here like a Swiggy and typically we talk about like a Zomato. All the vendors are now with the electric two wheelers because it's very cheap, and every petrol pump have a charging, swapping battery station also for that. Like so, that's I mean the concept is coming up day by day of the microgrid, and typically how it is going to evolve. I mean from legacy to microgrid. I mean we have earlier natural microgrid which call it like a DigiSat connected with other item also, then evolved to localized control, then distributed distribution grid, and we have a now dynamic typically microgrid. So day by day it is evolving with the different sources, and that is a traditional grid. And microgrid, of course, we have a bidirectional power flow. It means you have a local generation, maybe like you look into around the world, they say like a solar, wind. I mean, you have a typically the even a local consumers market, everything. So power flow is a bidirectional there. I mean, like because you can have a solar on your rooftop, you can consume and you can extra generation you can put to the grid. Like I mean, so we have a, in conventional grid, we were having a power flow only in one direction, but here we have a bidirectional power flow. I mean, and of course, we require communication infrastructures for the purpose of accounting as well as the identifying. I mean, in case of the microgrid, or even which really came concept from smart grid, but microgrid even you may not have a grid. Also, you may have a grid synchronization also like. So you have a autonomy of this. You have a generation, maybe local generation of different kind. Even people are trying like a fuel cell, then bidirectional inverter. Of course, you require then the software for control energy storage. Then you have a fleet of electrification for vehicle to grid, grid to vehicle. I mean, that's concept is supposed to come. I mean, because if you really have a tomorrow that concept to make the microgrid also as well as grid like. So why microgrid? Because it's a you can call it the electric and gas prices are fluctuating, and power quality and efficiency, reliability, and typically cyber and physical security. So technology innovation support to come with distribution generation, renewable energy resources, demand response, and grid stability control, or even on challenging part of it. So there are some objective of the microgrid. It improves the resilience of national electric distribution infrastructure, operate in seamless transition, islanding or grid parallel mode, and provide the interconnection interoperability of smart grid, and provide cyber security performance and data, and support power quality enhancement for connected load, provide two-way communication of frequency verification, data latency, and provide data management and system protection, and provide volt, VAR, frequency control, and support for interconnecting and island, enable dynamic load feeder reconfiguration, improve reliability for critical load, and provides outage management like number, duration, action, and balances distributed and central controller. It also enables price-driven demand response and reduces peak load for interconnected and integrate with the intermittent and variable output renewables also, and differs generation, transmission, distribution. So how does the microgrid work? So traditional grid connect home, business, and other buildings to central, but when part of the grid needs to be repaired, everyone is affected. So microgrid generally operate while connected to grid, but importantly, it can break off and operate its own using local energy generation in times of crisis like a storm, power outage, or many other reasons. And microgrid fueled by distributed generators, batteries, and renewable energy sources. Why? I mean, would a community should choose to connect microgrid, it provides backup for the grid in case of emergency. It can be used for cost. It allows the community to be more energy independent, and it can be connected to local resource that is too small or unreliable for traditional grid use. A microgrid can supply single facility, for example, Santa Rita Jail, microgrid in Dublin, California, and microgrid can power large area like, for example, Fort Collins, Colorado, and microgrid is a part of large load to create an entire district that produces the same amount of energy it consumes. Like, well, the Tesla recent work in Puerto Rico, Hurricane Maria devastated Puerto Rico power grid, and Elon Musk team constructed a self-contained microgrid for the hospital, and the hospital can now operate at normal without a connection to Puerto Rico electric grid. So at Hartsfield, the Jackson International Airport also power grid connection of the entire airport was cut due to fire, and microgrid connection could have saved the damage. So Chattanooga, Tennessee, is a city that well known for its focus on smart energy infrastructure, already developing a microgrid for its regional airport for this region. So now, who are the benefits from microgrid? The utility, better power control and reliability, reduce energy losses, because you have a local generation or local load, dynamic response, and realistic pricing model, increase demand, and customer, of course, prices for extended services and reduce prices and improve reliability. And society, integration of green energy sources like solar, wind, biomass, geothermal, and small hydro. Now, coming to efficiency, it reduces fuel consumption and supply close to demand, minimum distribution losses, combined electricity and heat, and reliability, openly manage on-site energy resource 24 by 7, and power quality and reliability at local level. Energy security give you critical for utilizing on-site generation and grid independence capability. And economic saving, of course, you have a peak saving, load shifting, supply management with demand response enables heading against energy cost fluctuation and reduction of cost of electricity with on-site, and sustainable reduction of carbon footprint by integration, cleaner fuel resources like renewable energy. And typically value proposition building on operator improved energy reliability and natural man-made grid interruption, cleaner electricity and reduce emission, and reduction of demand and time of user charges, and grid operator renewable peak saving, renewable farming, and ancillary frequency regulation, demand response, spinning reserve, and distribution utility reduces congestion on transmission distribution infrastructure, and power factor and voltage support. So there is microgrid applications also, like it can be an institutional campus site, hospital, university, commercial, industrial, remote off-grid community, military bases, data center, municipality, and can vary in size even from up to megawatt. Generation types of storage and investment can be significantly on return on investment can take only few years. So microgrid, it has a major component, like it has a master controller, match load with generation in both island and mode, grid connected mode, optimize integration, dispatching the control of distribution, energy source and load, ensure combination of PR economy, maintain the reliability and efficiency, and real-time response and fault protection, connect the disconnected from the grid, and predictive and forecasting analysis. And you can see how really the control here looks like. Now, fast and secure communication to monitor real-time network status, optimize operations and control of distribution and load, connect the building to YMS and BS, and continuous monitor trend microgrid component, help smart metering to obtain load NDR, electricity pricing and demand response capability, and continuous communication to utility and energy market. And these are, of course, the you can call it the major component like a energy resources, real production, how much percentage the typically a cost community and site engineering and construction and operational market. Right? And of course, what are the operational challenges? Of course, different type of sources like dispatchable and non-dispatchable, inertial and non-inertial, and different dynamic response of source like inertial source, slower response, non-inertial load, fast response, and grid because you have all in that and grid connected or islanding operation like a frequency and voltage control and power sharing. So problems in synchronization of distributed generation, ingress current like transformer, induction motor, like generator, three-phase unbalance like single-phase load, single-phase photovoltaic generation, and recent trends introducing many DC loads typically because they are more efficient like AC-DC or DC converter, introduction of DG with DC output like a PV fuel cell, wind turbine, micro turbine, gas engine, and needs for higher quality of power. DC coupled microgrid, DC coupled microgrid and nanogrid, and DC distributed power system, and synchronization and desynchronization with the utility grid. Of course, there have been some pilot project in Europe. These are the European pilot project in different countries like Greek, Germany, Netherlands, Portland, Denmark, France, Spain, and Italy. And smart power infrastructure demonstration in US for energy reliability. The goal of Spider, especially in US also, and typically these are typically US DOE renewable and distributed integration project in different countries like Santa Rail, Las Vegas, Port Collins, and Oregon. And this is how Hawaii Natural Institute of University of Hawaii supported 7 million funding for Department of Energy, 9 million from industry partner to make this smarter. And Japanese microgrid, there are also Japanese also 1 megawatt microgrid in Sendai project in Japan. Then the Aichi microgrid project, then another Korenja microgrid project in Japan, then Hachino a microgrid in Japan. So of course, there is a lot of project in China also as a microgrid standard microgrid in Nanjing Island. Then of course, this is a basic schematic of microgrid that you have energy storage. You have a grid with the synchronization, then you have a apartment building, single residential consumer, you have a photovoltaic with them, then you have wind generator, then single micro turbine, then fuel cell apartment. These are the possibilities like how really in the microgrid typically. And microgrid as Singapore also, they also try the microgrid concept in typically in Singapore, even a small country, and which have a in typically you have a wind turbine, couple of wind turbine, and solar 50 kilowatt battery also as well as grid synchronization and load connect. And of course, in India, we are only exercising the typically the solar with the of course wind also in that. And of course, there are some people call it a small kind of microgrid of different kind for solar and other. This is the first industrial solar microgrid commissioned in Gujarat. Typically, by ABB announced commissioning of in Vadodara. And of course, other microgrid in industrial, commercial, residential area, 2 megawatt hydroelectric photovoltaic complementary microgrid in Bantan usage in Kanai. Then the distributed PV generation control project in Hanai College of Finance and Taxation. Now, these were the some of the example of microgrid which are in the world tried. Now, coming concept of the topology of microgrid. Normally in a microgrid, you can think about what we can have a DG set, and DG set, of course, tied with the conventional generator with the AVR, as well as the doubly-fed induction generator. Also, Italy people have tried. And the wind turbine certainly doubly-fed induction generator is one of the we will discuss that, and permanent generator also, synchronous generator also used because we have a now variable. You can call it variable speed wind generation, which give around 50% more generation than solar, like typically. And then we integrate all together to have a AC combination. So, of course, problem in microgrid topology is the diesel generator because DG is very costly. And of course, people tried even, I told you, not only synchronous generator, but DFIG also to do the typically the increase the fuel efficiency of that. And of course, wind energy conversion system, like either by DFIG or permanent generator. Of course, people tried is 12 kg induction generator with the especially another contract with the double with the conventional synchronous cell and pole generator with the low speed and four solar power converter and battery energy storage system. A typical example like we have a DG set and then with the load and then you can have a like a solar with the uh, grid and then battery energy, wind also, couple of the wind with the PMSG as well as DFIG. So it has a lot of converters into it. Of course, you can reduce the number of converter by integrating, but at the cost of reliability. Like so that we conventional even a small hydro-based generation also have been there with the induction generator in the Himachal as well as the typically Arunachal and many part of the country earlier. Of course, they didn't use at that time battery, but now, I mean, people are start putting battery also with that. And of course, this is typically the similar concept like how you can have a in place of conventional synchronous generator, you can have a brushless generator, synchronous reluctance generator, or you can have a typically voltage frequency regulation and power quality improvement using only one voltage source converter. You can integration of the DC side also a voltage source converter. Now coming to proposed microgrid topology, which really we look into, especially, I mean, this is probably I think around 8 to 10 years back. I suggested to one of my typically friend student, especially in Canada. I mean, with the hundreds of topology, and there is a couple of people making transaction on sustainable energy. I mean, this appear in that. So concept was you have a DG set, and you might have a typically like a wind energy with the double the converter. I mean, why we have a typically the wind with the variable speed. I mean, double converter we are using in spite we say power frequency is a little delicate, but we use in all cases double power converter because wind turbine we have to force to run at variable speed. And I asked couple of my students to even take a data from the site from Tamil Nadu of 24 hours and then they use the variable speed generation and we found 50% energy from same wind blowing. You can generate more 50% more energy. But in that case, for small cases, you can use permanent brushless DC generator because it's a cheap and very cost effective also. They are easily available now at the probably with the from the neighboring country. So you can have a even a typically not only synchronous equal you can not necessarily synchronous generator conventional kind you can use which is shown on the right side but you can use typically permanent synchronous generator or squirrel cage machine or synchronous reluctance generator because they can give you the sine wave voltage and the voltage of that because there is no control then you can use the voltage control form even this converter also by providing reactive power as well as other features for the so we have a variable speed DG set with the constant speed diesel engine as well as variable speed wind turbine. I mean, typically, if you look into with the different generators, I mean, or we can use the DFIG also. I mean, people are using even for 50 kilowatt DFIG for even telecom tower also, even India and worldwide, Brazil. I mean, all the places. I mean, like, and then or permanent synchronous generator with all these generators, with of course double the converter there, or synchronous reluctance generator, which are coming up now very quickly. For maybe we launch the synchronous reluctance machine for up to 350 kilowatt already because it has given a higher efficiency even for water pumping. It has given efficiency 4 to 5%, especially like a solar water pumping because you operate always with the inverter. And this machine is a really a very recently introduced, hardly less than 1 decade when it's the outcome of the permanent synchronous generator with the silency, especially flux barriers. I mean, but it's a very you can call it robust machine. I mean, only the some I mean flux barrier are created in typically in conventional cylindrical kind of a cylindrical machine like or you can use the variable speed different kind of generator like a skull cage different machines and even on DG set also you can use different machine because your power electronics can control the voltage and frequency of local grid also without any power so you have a large number of options typically you can think about in that for wind as well as DG set with proper control. So that these are the configuration we evolve with the different machines. All I mean like a squirrel cage machine, permanent brushless DC machine, permanent synchronous a synchronous reluctance machine, as well as the conventional synchronous generator, as well as the DFIG, like so which you can think about otherwise like I mean. And the battery is certainly on the DC link of these two converters, like you can think about like also, these are typically with one source. I mean, like this variable speed one turbine of different configuration. Then we have a typically you can call it. I mean, the many configuration, or you can have even kind of solar also. So this is with the one with the wind. Like so, we took some case study. I mean, in the our research student work out with this, and we took first as a DFIG. I mean, my around I think around 10 PhD student work on DFIG now and this was the initially asked couple of students to go ahead interesting control with the islanding mode. I mean, most of the DFIG you might have seen the literature is grid connected one. But we look into the typically standalone mode and the couple of converter in between put the battery. An interesting part here that to get the MPPT, there was an interesting challenge that you have to have a voltage control at the voltage control for providing this state side converter that it can take care of the non-linearity of the load also, and transformer can provide the wire also, because we normally put the transformer on because this power electronics is at low voltage normally. This is more less than half the volt, because you might have seen most of the one rotor machine, the rotor voltage is half than the stator voltage, and apart from that, we operate only up to 30% slip. It means half multiplied the 0.15, it becomes like a 30% slip means around half 0.3. That becomes 15% typically the voltage on the rotor side. So then the device rating, voltage rating can be reduced and cost can be reduced also, and become more safe also to operate like typically. So we work out with this, and it was very interesting challenge. I can tell you, you have a typically frequency control here as well as the voltage, typically frequency control and MPPT also. In DFIG, we have two variables. One is the slip, another is the, you can call it the speed typically. So by speed control, we have the MPPT, maximum power tracking, and by slip control, we control the frequency. So that's the concept we have given first time around decade before by my first PhD student, Dr. Salim Sharma, who is a professor now in AGTS Indore. He worked out first, and then many other students use the different concept for typically and different algorithm, typically filtering or so. And this is something this student I worked with using the fuzzy logic for even for maximum power tracking from the solar, and then providing the typically control for the rotor side converter for regulating the frequency and as well as the maximum power tracking. These are of course the concept to go ahead with the typically speed control for maximum power tracking, and for voltage typically control for giving reactive power from this converter only, so that you not give a much reactive power for, at least for machine reactive power we give from the rotor, because the advantage of giving reactive power from the rotor is only you have to give slip times the reactive power. If you give the reactive power to induction machine stator side, you have to give corresponding to 50 hertz a full amount of reactive power, maybe 60% of the rating normally. Even power factor of the induction machine is around 0.8. It means you have a reactive power from stator side 60%. But from the rotor side, this goes slip times. So, I mean, the slip is like not maximum more than 0.3. So your reactive power given from the rotor side is hardly 30% or even much lower than that typically. And at synchronous speed, it passes through synchronous speed. You can understand synchronous speed. We don't give any reactive power. We give a DC current into like a similar to conventional synchronous machine. So that's the concept. Like it's gone to that voltage control. Also, we did typically from the your rotor side reactive power current also. And this was, of course, experimental setup. We worked out initially. Later on, we procured around, it was 5 kilo, typically the 4 kilowatt machine from, we got from 19, probably 63, and it's still working very well. I mean, from UK. But now we have a 3 more 11 kilowatt DFIG in our laboratory, which really procured in 54 lakh. DG set with the 11 kilowatt skull cage machine with well vacancy drive to simulate the wind and all that. So many students were working with that. Even you are feeding the non-linear load, but you can understand the stator current. I mean, that was the sinusoidal. It's not affected. Load have been non-linear and voltage have been also sinusoidal. So voltage TAD hardly less than 5%, as well as the stator current TAD also 5%. The initial is feeding the non-linear load. I mean, so these are experimental results from the laboratory setup of our student, and this is the speed variation. So when it passes, I mean, you can see the probably the, I mean, in between slide of the second row, that the when wind speed goes from low to high, you will find it passes through synchronous speed, and it changes the phase sequence when it goes above the synchronous speed. But at synchronous speed, it becomes the DC currents into it. Like, so it was very interesting features we look into when you change for wind generation. I mean, speeds you change and it goes to typically from sub-synchronous speed to synchronous speed. And at synchronous speed, it works as a synchronous generator. And it feeds the non-linear load, but machine is not affected. You can say machine current is sinusoidal. I mean, when you introduce the control, I mean, typically you can see on that how we really switch on the control. And typically the wind speed decrease, increase. I mean, these students work out with the experimental setup of the W-fed index generator for maximum power tracking of wind application also. These were the some of the observation. We are able to operate it satisfactorily without much problem. And TAD of stator current and voltage have been achieved within the limit in a standalone operating mode also. This is the other configuration. Our student took it like permanent synchronous machine. We have all the machines with us. I mean, in the laboratory we procure in last couple of decades. And the battery we put on again DC link, and now we introduce solar also on the DC link, like with the of course boost converter with the MPPT. We are able to do MPPT of the both. I mean, like even of wind as well as solar, and able to provide the electricity to the local with the inverter, like energy stored in the DC link. So that is what you can think about the minimum. Of course, the PMSG operates it in vector control mode with the sensorless control. We sense the current and voltage only. The voltage of DC link we estimate, and we use here the estimation of the speed as well as position, because it requires position control also for this. So we are not sensing anything from the mechanical side, neither the speed nor the wind speed nor the more machine speed. All we sense from, I mean, estimate from the electrical side. So that have been a very interesting challenge. I mean, the different work out for that, like and of course with the solar we put on the grid, like and these are of course the design equation for wind as well as the machine, wind turbine and this BMS machine. This is an important characteristic you can think about. If we put a straight line from 12 meter per second, you will find you are not able to generate much power typically at lower wind speed. But typically, at you look into at if you go to typically at 7.2 meter per second, you are hardly having a zero generation. But if you go to the variable speed, you reduce the turbine speed to 60%, you're able to get 20% generation. And even at even where you are having even a like a, there is negative power supposed to be there also at 66 meter per second, we are able to have 10% power generation. So this on the peak of these lines, we have to operate this wind turbine forcefully from the generator side. Mechanical side, we not to care about, like, I mean, also. I mean, from electrical side, we estimate the speed of the rotor as well as control corresponding to that, it generate the maximum power. Similar to any MPPT technique, we put similar to that what is the generator is generating properly, like also. And these are, of course, the control that people have used sliding mode control or different observer for estimating typically the different parameters which I mentioned it. You can estimate the position as well as speed, because position and speed both are required for this one, typically for permanent generator or any even your conventional DFIG also, like typically. So these are typical control. We have MPPT as well as the control of this your machine side voltage source converter, like these of course control load side. Load side we have to regulate the voltage only, typically, and frequency and voltage corresponding to in a spite we feed the non-linear load or linear load from the converter. So converter current are drive and control of it. And these are of course the different control our student have used, like typically your sliding mode control or improved versions of sliding mode control for getting a fast response. Typically when wind speed changes from one position, typically one value to another value without chatting or without oscillation, like and these are of course you can see how the typically the angle, I mean speed and angle are estimated, I mean in different case, and how the typically you can call it the wind generator currents are balanced and sinusoidal without much power operating typically at two different speed, like and then even feeding the non-linear load, you can just see when the non-linear load is fed, and certainly the power comes from the battery if generation is less. But load is not affected, like load voltage remain constant, like but generator current accordingly will change from the generation, like then we work out, of course, with the variable solar also. So all cases you shouldn't have considered. All these are experimental result practically operated in the laboratory, because we have a lot of, I mean, even the different. We have a 20 solar simulator in the lab, and we have a probably more than 10 wind generation also in the lab. Like load change, the voltage is not affected. I mean, typically, or as well as the generation in low demand also not affecting the performance. Like this is another configuration. Our student I asked that you can take a small ITO with the skull cage and typically a capacitor, but this voltage source converter can regulate the voltage, and then we have a wind turbine also here in this case, and battery connected on DC link of this. I mean, so we are able to again have maybe small wind and maybe small hydro like a run of river or canal. We can put such system, but very robust generator, skull cage induction machine, and permanent generator for the wind application with the boost converter. And we do MPPT similar to like a solar in that case. Like so it worked very well. I mean, he was master student Krishnant Balla. I mean, who finished the PhD from MIT and joining probably next month to us as a faculty member also here. Like he work out for master degree. I mean, typically long back or so on this system is power control, like I mean, frequency control as well as voltage control. Both are exercised in that. Typically from that converter, which voltage source converter. This was the for wind because this permanent pressure generator it worked very well with the typically with diode rectifier by boost converter, because that keeps the current Cauchy square wave. With permanent brushless DC machine, it your Cauchy square wave, like. So we look into with the concept of many other machine operating many application we also use here also for that same purpose here, like I mean also. So some benefit and we work out here. I mean typically you can say uh, the voltage is not affected. I mean the typically and it work with the skull gauge machine. Current distortion was also not there, and in we are feeding in only in a load as well as typically without much problem it work without, and the TAD of typically we are able to get even the your skull gauge machine current TAD only 4.4%. We introduced in skull gauge machine one interesting concept also that we operated that machine out of saturation because of control we are able to maintain. Otherwise, in open loop, it is unstable. Like so, that's also we look out carefully without any problem. And this is the load thrown or load direct and the wind. Typically, in all cases, the terminal voltage are not affected. Even the load thrown are or even a generation varying also under those conditions. Then we took another configuration with the again hydro with the three phase synchronous reluctance machine with the capacitor bank, and then we have a solar as well as battery on the DC link. So MPP for solar and hydro we are generating for maintaining constant frequency, constant power. Even the hydro head changes and the voltage and typically this voltage source converter is responsible to regulate the voltage. It's responsible to I mean typically compensate the nonlinearity of load also and maintain the your is called is the synchronous reluctance machine current sinusoidal and balance also. So this has a lot of responsibility, this voltage source converter in this case, but we are able to have only one battery energy storage, which also regulate the frequency. If load is varying, intermittency battery takes off solar as well as the load, as well as of course varying generation even from battery also. It worked very well. I mean typically, and this again another different work. Uh, I mean they operated experimentally also in the laboratory very perfectly. We have all machines, synchronous reluctance machine also as well as even other machine, brushless machine also. Like these were the control, I mean frequency control and voltage control, and work very well without as much problem. When a DC link voltage control on the battery, we work out because battery was using an MPPT of the solar also taken care, the proper design and all the control equations here. Like I mean, so work out. And this is a typically experimental result where they put the machine, synchronous reluctance machine you can see here, which is coupled to with the induction machine. We have a well frequency die to lies typically with that and PV array. So you can just see here we have a TAD less than 5% of the voltage in spite of nonlinear load, and the generator current TAD was also only 3% here, like and operated in different operating condition mode with a nonlinear load and varying solar insolation also. It does not affect the performance, especially for the load voltage and also. I mean, typically when you have a very kind of nonlinear load, we switch on how really it goes for also. Another topology we took into, I asked, I mean, these students to work out with this topology for dynamic load, not only the typically the non-yield load also, because many cases, I mean, in a remote place, you might have a even a motor maybe for either the floor mill or you might have a typically water pumping system, or you might be having a even a typically the pump. I mean, typically on same microgrid, so how really performance is there typically of this total microgrid system. So this was the control, of course, with the typically of the regulation again voltage and frequency from these. I mean, they use typically kind of non-linear. You can call it the kind of adaptive kind of control for voltage and frequency control of this system because it is all it is a DC link voltage control from the battery. I mean, like also, and we are able to operate satisfactorily with the only very less TAD 1.6%. In spite, there was a non-linear load having TAD of 21% of this case without much problem under varying load, a varying situation also. I mean, you can just see motor starting here. I mean, which is not too much affecting. I mean, the typically the voltage, if you look into right side, what is not too much affected when I mean your dynamic load is connected. I mean, because it will draw little larger current, inverse current of the motor, so still this will get an unaffected voltage also. Typically, you can just see there. And converter takes care with the battery this inverse, but load is not affected like also. And these are of course high the power consumption the battery, and typically that takes care dynamic load variation as well as typically the non-linearity of the other loads also. So these are all experimental results. These our students really work out successfully operation of these systems. I mean, like typically removal of load, application of the load, change of solar generation. I mean, like and motor starting also typically. I mean, all these cases. So then we took another one that we have a typically solar there, then wind also there, and then a small hydro. One thing about three renewable energy sources, all three with the one battery and connected load on AC side. With this single voltage source is able to manage voltage regulation of this as well as to meet the skull cage induction generator reactive power requirement and frequency regulation also. Like of course, with the support of the battery, you can take power from the battery, you can feed power to the battery. But the wind, variable wind speed as well as the variable generation from solar, it comes to DC-link, which charges battery if it is a surplus power. Otherwise, it feeds to the load. Like so you have a to all intermittency of the load, the wind generation, solar generation, is taken care by the battery only. And but we are using only one voltage source converter. You can think about with three sources also. Also. It work out very well without any much problem. And these are the experimental results. We really able to operate with the non-linear load also because these shouldn't work in, but source current, generator current were balance and sinusoidal without any much problem. Even when you change the load, when load is or wind speed change, or solar generation is change, load is thrown, they still work without any problem. The terminal voltage was really constant frequency and constant voltage without any much problem in this island. Then we use conventional synchronous generator with the solar. This example I asked to one of my students to look into, like we have a hospital and we have normally the in a hospital the DG set, but we can install the solar on the rooftop and the battery also there. So we can reduce the diesel consumption in that case. Like even the grid, if it is not there, the reduction of the because diesel cost of electricity from the diesel is around 20 rupees per unit. But now we are getting solar less than 2 rupees. So, with this, we can probably think about even if we, for the period we operate the generator, we should operate almost like more than 80% load for the short period because here we have a battery. We not to operate the generator for the partial loading conditions like also. So we are able to work out, this very successfully for practical kind of the situation there. And this was the typical control for even if we have a non-linear load, and then the control of the typically for the generator also with the AVR and all that for again isolated mode and typically. And we are able to get like even you can understand if we really we use the non-linear control how voltage was distorted, but when we start putting this we switch on the TAD of the voltage reduced to less than 5%. Like you can understand when you put the non-linear load for DG set, they really distort the terminal voltage. Also, reason being because synchronous generator have a very large, you can call it the synchronous reactance. So if you draw the harmonics current from that, drop will be much larger than the grid. Grid does not have that much source impedance as your synchronous machine or conventional synchronous generator have. So once we put the converter, this system on with the converter compensation, the terminal voltage TAD also reduces less than 5%, as well as the DG set current TAD also reduces on that same converter. Like we are able to operate successfully without much problem. That you can see, like without without compensation, how the DG set by their feeding non-linear load and what switch on of DG set is able to reduce the TAD of voltage loss also less than 5%. It was very interesting what we look into experimentally also. We work out earlier a lot of work with the simulation, but this we work with the experimentally also for solar generation, variation, load change, sudden load change, how really it's get affected the system. But you can see terminal voltage is not affected at all in that case, like with the voltage and frequency, and these are all control instruments. Though another with we work out with the wind also with the DG set as a kind of and with the battery connected there, and that was again the control with the DG set properly, and we work out successfully maximum power tracking with this and with the DG set also it satisfactorily, not only with the grid like typically, and we are able to get TAD even under non-linear load also not much higher TAD of this system like and work out under wind variation also, load variation also, and motor starting. You can just say how the induction motor is started and how the battery current is take quickly through the converter. So converter current little bit increases. Like also, uh, but the voltage is not affected. You can say terminal voltage remains constant as well as there is no dip or so this was interesting control. We are able to do very fast control of this converter, which have a battery on the DC link, and even during the starting of the motor also, as you see in that. So we took another with the, DFIG also. We put not only battery on DC, but we put the PV array. And you can understand if wind is not there, we can open the stator of it and use the converter, this load side converter as well as solar and typically the battery for feeding the non-linear load. And typically, if required, we can use the digital tools also. So more the research, I put couple of PhD students for the synchronization. We couldn't get you will not surprised that we couldn't get experimentally any synchronization. We will talk about the typical the contact or circuit breaker to operate or connect. But you can say in that case the converter was at stake. So I asked my student to use the solid state switch with the typically a different configuration of IGBT switches. Initially they blown some, but later on I told you have to be careful about the control because these are the delicate and they're able to get synchronization standard says around typically around 10 cycle. We are most of the our students are able to get 3 to 5 cycles. We are able to synchronize very well either DG set or the D5G also because these were very interesting study because both the machine either digital set conventional synchronous generator or DFIG both have inertia. So to change the frequency it was not so easy to quickly I mean from that because we have to control the DFIG voltage only from rotor side converter. It was very interesting I mean to synchronize either with the DFIG or with the DG set also in this case like typically, and it worked very well without any much problem. I mean, these are the typical control they're able to use, but many time I have to even not only sit with them, but I have to stand in the laboratory environment, also go there and really stand with them to work out that it work very properly. And these are, of course, the result with typically the how the solar generation battery increase the charging. Also, it work and the FIG also for the wind how it goes really to from subsynchronous to supersynchronous, and you can clearly see how the current changes. So to show the rotor, we really took a little compressed result with the typically 2 seconds per division or so, which here have a capability of. So, but TAD of the voltage was 4.2%, and the induction generator current TAD was 2.9% only. Typically, we are able to operate successfully. This is another case that we diesel set we took about synchronous reluctance generator and then permanent generator, generator for wind and solar. And interestingly, this single converter is able to voltage source converter is able to do, I mean, the voltage regulation, frequency regulation, as well as even typically feeding the reactive power harmonics for the load as well as unbalanced current to the load also. All those, I mean, situation we are able to take care of this, I mean, without any problem controlling this total system. Like, and they use very interesting control also. So this is non-linear load are fed from this, but the source current you can say the TAD of this was quite low, typically, I mean 4.9%, but where the TAD of voltage was only 1.1%. So this synchronous generator was not saturated. When machine also saturated, it also have a little distortion in the voltage also. And also we work out that we force this machine, especially brushless machine, either squirrel cage machine or synchronous machine to operate at unsaturated condition by reducing the voltage. So if you really operate in without converter, I mean with the capacitor, they may be unstable, like okay. But with the converter closed loop control, we are able to make this unstable system to stable also in controlling properly. And then you can see the performance where load removal. It does not affect the even generator current because it was driven typically from the your DG set or hydraulic and the induction motor is starting was not possible. But when we put the converter, it's able to start successfully without any power. Then we have gone autonomous with wind and solar and DFIG working. This we already talk about a little bit on that. So here also we're able to get very satisfactorily about operation of with proper control with the maximum power tracking as well as I mean the even if we use the direct torque control, we call it here power control virtually. Torque for generator we call it direct torque control. We call it direct power control. I mean typically other than this concept was another one then other than vector control also we use it there and DC converter for and this was the typically their hardware setup and you can see the TAD of typically and the voltage was only 4.2%. I mean, like also, and the variation of speed variation of D5G and all. And we look into typically here again, I mean, the wind turbine driven from conventional synchronous generator. The reason being, Enercon is manufacturing synchronous generator, conventional silent pole synchronous generator without gear. Because that if you take a conventional synchronous generator, it's without gear, but you have a typically variable speed. And this is the foreign did for her PhD work in that, and we have a solar as well as battery in between, and then we have a typically the load as well as grid connected, so we can feed to the grid also here without any problem. And it work out because this conventional synchronous machine was first time imported for with proper control. I mean, for current control also they use it typically the not the PI controller but the typically the kind of intelligent control for the current control also like typically. So these were the all MPPT technique for that. And these are the experimental result. You can see the opposition estimation for control of these machines, synchronous machine. I mean, we are able to get accurately and voltage and current are properly all sinusoidal, typically. I mean, with the non-linear load also it work well. The inverter takes care, and DFD voltage was 19.9% or so. All these experimental jet also. And variable wind speed, solar variation, load variation, load change, all the eventuality is observed in that case. I mean, in all these experimental studies, like and TAD of voltage was 2.2, around 2% only, even when the you have a non-linear load operating under different operating conditions. Another is a I mean, because it was like a seamless islanding and synchronization. That was more important. I consider ask them to that to with the grid also. If you look into here, we have a solar transistor, battery, and the converter. And now here the battery, why it is put that you have intermittency of the solar, you have intermittency of the load and intermittency of the grid. Grid may be there, may not be there. So, I mean, typically in that case we work out. I mean, typically with proper control of synchronization, also voltage control, because I mean we don't want to push the grid. You can't push it. You only converter. You have to push towards that. And we work out with the proper synchronization technique, checking the voltage frequency as well as the angle. Then only you can probably work out properly with the proper control. And this is you can just see how the synchronization taking place after the 4 cycles. The typically grid current start flowing like I mean also um, here and the different even the under the load variation also. So TAD in typically of grid current also and for hardware synchronization also we work out they work out that this is when the grid is gone. I mean like and when grid has appeared. So here the resynchronization of the grid. You can see the grid came here and after 5 6 cycles we are able to synchronize the grid and the current start flowing into the grid. But you have to estimate the angle on the both side. I mean typically the grid side as well as the on the inverter side or your local microgrid side also, then only you can synchronize. It was interesting story for all these synchronization. Initially, they blown off a lot of devices, but finally I have to stand with them. And after that, they have been very cautious with proper control that there is no issue of in synchronization. It was only the solid state switch we put for as it is on, and the TAD of course was quite low, typically of all typical waveform current and voltage waveform around 3%. Then we work out again with the here also another case study with the we put battery on decilling of the solar which take intermittency and non-linear load and the grid also. So here also they work out with islanding mode and synchronization mode properly. I mean without any and this is the synchronization algorithm of course angle move towards that and we move the angle and frequency and then put the logic to solid state switch which really synchronizes the converter also. And this is you can clearly see here how the synchronization typically switch comes and current start flowing, and how here you can see the terminal voltage and the grid current start flowing on the synchronized. So the grid came here. This was the load voltage, load current, which is not affected, but grid came here, and then after 4 5 cycles, we are able to synchronize the grid without any tangent. Like there was no tangent associated with that, and how the angle are coming closer when we close the switch. Like so, this is the typically islanding and synchronization control. And TAD, in, of course, in islanded mode also was not more than typically of the terminal voltage 2%. I mean, this was in island mode operation, so voltage TAD was hardly less than 2%, even with the non-linear load on this system. And then typically the load involved and typically load application. And you have to estimate frequency, voltage as well as all in that case. Then typically the solar variation also. And we took, of course, the you can call it wind as well as solar and then synchronization to the grid with the combined output battery there on the receiving. So you can say what we were using the switch here, the back-to-back connected IGBT switch. I mean, like the synchronization. You understand if you really abuse, then this goes out of order. Like they are able to operate successfully with this algorithm, as you see on the left side, and we are able to work out without any much problem. I mean, like they typically under steady state, even under non-air load. I told you it work very well without much problem and MPPT also of the solar and typically with the solar variation, load variation, and then standalone mode. I mean for this period and then synchronization. So islanding here because of the they calling grid fault, but we say grid disappear, grid distortion is taking place, and then 2 3 cycles we're able to connect to reconnect back also in different conditions like here. I mean and typically then we are able to extend further wind also into solar battery and then get synchronization with another kind of control is to work out with that like properly. So non-linear load and typically the again the typically the get synchronization properly. I mean like here this as you can see here the load application removal and then the typically the different kind of, and the synchronization here. You can see how the synchronization taking place and how the angle is going on. Both the angle are going closer to it. Then only you can close the switch. Otherwise, you cannot close the switch. Like so it comes out of phase also. And then you have to bring the inverter closer to it so that they synchronize, and then only you can close the switch also here. This was the interesting. I mean, like then we took a small head because machine on. It was interesting that we have a battery, we have a solar as well as the machine. So in presence of the machine, synchronization was really tough. I mean, like you can understand. I mean, because machine have inertia, so you cannot do quickly. So battery as well as typically battery is responsible to increase the frequency or decrease the frequency of this system, and then we are able to synchronize with typically. So these are synchronization, the what voltage, frequency, angle, all we have to, and then only the getting signal goes to this switch also. Also. So these are typically the, of course, this guy have I'm tech guy itself published an IEEE transaction on sustainable energy, this synchronization algorithm like I'm not. And then this is typically what we say synchronization to the grid and synchronize of the generator also for that. I mean the converter is responsible. So we have a here DG set, we have a grid, we have a wind, we have a solar. I mean you can synchronize either the grid or to the DG set, any one of the two from the reliability point of view, because you may not have enough generation from solar and wind, so you may require DG set on the side. Of course, with the battery, so we took consideration of that into here. I mean, like typically I mean the load compensation, then the voltage regulation, then angle calculation. When angle comes closer, then only you can close the switch like that. So these are the typically simulated result that how grid comes and synchronization take place, and when grid is set. And these are typically experimental results for come to that. And then the typically how the synchronization take place here. The grid current is start coming. And here also you can see after few cycles, load voltage and load current are not affected. But when the grid comes, after few cycles, we are able to synchronize after around 4 to 5 cycles. Our standard says around 10 cycles. Of course, desynchronization, you just open it, it work very well in voltage control mode. So we have to change the algorithm also from current control mode to voltage control mode, and it work very well without any problems in that case. And this is again the even the machine we have a, I mean the even a this machine DG set or the grid which I told you can synchronize with this or you can synchronize with this depending upon requirement, and of course you have own local microgrid also operating with that. But battery takes care of all features of this, so this is typically control of all machines here. I mean like and experimentally typically the kind of synchronization also. And the load change, all those things are there. And here you can see, I mean, the grid appear here, but it was out of phase. I mean, all experimental. Then it move the your system move towards the grid, and when it comes all both equal, then we synchronize it to close the switch, and grid current start coming. I mean, like there, and it work very well without any much problem. Then coming to, we really ask my student to look into for charging infrastructure. I mean, for tomorrow electric vehicle will be coming up. So that's also we look into that. Okay, we can mainly have a solar, you can charge on the DC side or you can charge the AC side. But of course, if vehicle is not there, you should be able to feed to the home load also. So you can take power from the grid also. So that's also we work out and work lot of interesting logic. I mean, and work satisfactorily that converter is able to work for the grid. Quality improvement also extra generation you are able to put to the grid also. So all these are the logic. But here we look into a small. You cannot say like you have a storage battery, you have an electric vehicle charging, so you cannot say today solar is not there here too. Grid is not there. You cannot say your consumer of a small vehicle like I foresee around a decade before that. I mean, lot of like a two-wheeler, three-wheeler will be there. So you must have a small, see, a small generator also here. And we took a skull cage machine with a DG set with the specific advantage that we force this machine when we connect it to operate even fairly stable voltage mode with this converter. So this converter have a lot of responsibility. I mean, to improve the power quality of the grid also when these all non-linear load or vehicles are there. Or with the DG set also, it does not draw any harmonics or reactive power and regulate the voltage also this islanded one. The main source of have been for the wind with the battery, the solar with the battery here. Typically, we work out and it works satisfactorily without any problem. Like I mean, these are the control, and you can see the typically the all typical results have been quality improvement and all those have been there very satisfactorily with the synchronization and islanding also. You can just see typically if come to be, I mean, different power chain or so. We work out with the solid state switch also, different kind of switch we work out, and it work very well without any much problem. I mean, dynamics and all that, like typically islanding, synchronized. And then we extended this concept to three phase. That we have a battery, we can have a wind on DC link, we can have a even a vehicle also DC link, vehicle can have a AC side also, DC side also, or we can have a home load also. And typically we can connect to the grid, island from the grid, and we can have a typically solar. So extra generation from wind and solar there can put through the grid. I mean, or when battery is fully charged or otherwise, and battery also takes intermittent. So this was interesting part. Like I mean, it work out. So and even synchronization islanding, we are able to take care of solar variation, wind variation. Typically, all the cases we are able to, and then you can see if you are not able to switch on the converter, how the grid current were there and voltage were distorted. But when you switch on the converter, then the grid current becomes annual and voltage also improved. Like as you can see here, and then typically your it start working as active filter when you switch on the this system. Typically, even off the grid also. I mean, so this is another configuration we work out for again for this same charging infrastructure with the typically with the for electric vehicle charging infrastructure and with proper synchronization and idling. This was the one of the strength, especially the synchronization and operating. I mean, like you can just see how it is getting synchronized. Like it grid comes here and then it's synchronized and grid connected. But load voltage and load currents are not affected. Load is not affected. It is only you can connect the grid and you can island. That's one of the very important property for the microgrid. And this is with the typically PV array and battery, and you have a typically the on AC side and DC side also you can have a vehicle charging also. So this you perceive that after few years you will have a charging station corresponding to that also. And then of course you may have a home load of different variety and vehicle on DC link side also. And with a lot of interesting logic work out. So with this I would like to, I mean this is conclusion I would like to typically converge here. And these are the some of the our references and our student paper also around. And thank you. Sir Abhishek, it is back to you. If you have any question, I
Yes.
will be happy to answer. Okay.
Hello.
I don't know. Yeah, yeah.
Thank you very much, sir. Thanks for delivering a wonderful session. And I would like to take some questions from the
Sure, sure.
participants.
If I can.
Participants, you can put your question in the chat box. Uh, for very few minutes, we will allow participants to ask questions because we are quite, that means running short of time to start the second session. The participants, please ask question in the chat box. I will put on your behalf to sir. There is one question, sir. Homer Grid or ETAP software which is suitable for microgrid system simulation. That means he wants to ask, there are two softwares, Homer Grid and ETAP. Which one is more suitable for microgrid system simulation?
Actually, the Homer, which one of my students work in energy, I mean, those are from design point of view, okay? And the power flow. What we work out here, we work out on actual typical physical system. Are you able to follow? Like, I mean, there you take either you take PSCAD or you take a Homer. I mean, they don't work on the component level, now. I mean, like a synchronization, although those software don't do. It's only for the typically the design concept there, okay? Energy calculation, other things like. But actual real control, it can't do that way. Are able to follow? So we work out the typically the control. I mean, let's say in deeply. I mean, especially the synchronization was very enjoyable there, as well as the synchronization. Not only the control was also reasonably enjoyable with the different machine and different configuration, but those software. I mean, this work and our work and that work is totally different. I mean, that is from you can call it like a from design point of view. I mean, those work on the basis of RMS and all those. Nah, I mean, like the actual physical system control cannot be generated from that. Like, I hope you understand. Like, I mean, what
Yeah, I hope Mr. Ravindra Kisan Rao Mankar, who has asked this question, have got the idea. And sir has explained in a wonderful manner. I hope so you are satisfied. Now the second question, Mr. Shabya Sachi GK, what are the research area or problem statements suggested for researchers who are yet to start? That means he wants to take some direction from this session. And this question is in that manner only.
No, but I can tell you like a microgrid application day by day are increasing. You have like a 5 lakh telecom tower. Okay. So there we so far we are putting DG set and battery. Are able to follow, like, I mean, and the grid is there. Some places grid is not there. You can understand. We can't forget the mobile call in spite the grid. Let's say grid is not there. So you have to provide a reliable power. But the question is DG cost not only the pollution, maybe little. I mean, city also we have a telecom tower, but the more important is the cost because electricity is 20 rupee per unit. Now here we have a renewable like a solar with 2 rupee per unit. Now 1/10 of the price. So you have to integrate the solar with that. I mean, typically, and maybe if you have some battery with the solar, it's not necessary to run even the DG set also. So now you can understand if you are using a DG, you have to synchronize with the DG, you have to island from the DG, and you have to control this. I'm giving you just an example. Typically, I'm talking about only telecom tower, which are 5 lakh in our country. Okay. So similarly, you might have be having tomorrow charging station in remote places also. I mean, maybe in the village where even the electricity may not be there. Even I'm very close to, let's say, the state called UB to which I belong. I mean, even Chief Minister Mr. Yogi said you will get electricity in the village rural area 18 hours, but 6 hours is not there. But there are a lot of activities for 6 hours also you have to operate. Na? You cannot forget about. So there also you have to put like kind of microgrid such system for charging infrastructure, rural power supply system, rural lighting system, other things, other activities, or even the market also, or many. So there also, so you can think about what really you go on adding the sources there, and with the power control. You might have a DC generation, you might have a AC generation, and AC also like a wind. Now we have a variable speed. So certainly you put a lot of power converter into it. And power converter you have to operate very, I mean, you have to control very carefully. I mean, otherwise you will blow the entire system. Na? So there is a lot of interesting, I mean, in case of microgrid, if you really work on application base, now you take a particular application and build up. Like, I mean, we're talking even to some guy typically now solar, they want to integrate to 1 crore installation. Na? I mean, without the grid, like, so you can think about really entire home. You can operate with the solar, with a battery. Okay, so it becomes like a good microgrid, and then grid appears. You can synchronize it, you can island it. But many places grid is not there. But you cannot change the complete load also on the home now. I mean, maybe a pump is there. You might be having a like a non-leak cooking, lighting, other appliances, delicate appliances like television in the village also. So you have to give electricity to them. So that becomes a interesting microgrid that you have a battery as well as you have a solar. If other sources are not there, like, I mean, typically. So I mean, if you really look like a such kind of example, you have a thousands configuration of the typically the microgrid, which really you like to do the research on that. Like, I hope probably I think partly I'm able to answer it or not.
Yeah, sir, definitely. And I hope so. The participant, Mr. Sabayachi GK, you have got the your answer.
And if you have a like
As
you have a very fast control, then you should be able to even reduce the energy resources also. Now, like a value of capacitor, you can reduce it. Some of my students work out on that. Like, so that
yeah,
control is the strength there. Of course, we are not the people of control. We are people of typically of, let's say, power electronics as well as the maybe the machine and typically, but you can't avoid this. All the things goes with the proper control. So we have to work very, I mean, interesting control also into it. I'm like, awesome.
yeah.
Okay.
Yes, sir. Thank you. And one more question, only one question we will take here now. How does the inertia will affect, Mr. Sanoj Kumar is asking, how does the inertia will affect to the stability of microgrid?
Well, here, couple of my student. If you talk about it's a solar and battery microgrid, na. So my student have worked out, one PhD student work out, who is now faculty probably in IIT Dhanbad. He worked out with the emulation of synchronous generator, inertia from solar inverter. Okay. Another student who is in doing the job in GE, he was also from power system side, work on hardware. So he worked out the induction generator inertia emulation from the solar converter. So there is a lot of work like where you can think about like this. I'm talking about how you can generate the inertia. People worried now. When you have a renewable like a solar, the inertia will be the problem and all that. But when you have inertia, then converters should certainly able to push the machines. Now I've shown the example. For example, where machine were there, I told the DFIG along with the converter, I showed the synchronous generator with the converter that how really you are able to pull it to synchronize to the grid. Now, so that with the, of course, because you have an energy storage like a battery and with the converter, you'll be able to take care of the inertia issue also without much fault. Like, also. Now there is a lot of literature on the converter emulating the inertia also into the system. Now, typically.
Yes, sir. Thank you very much for your wonderful answer, sir, and wonderful session. You have explained most of the nonsense of the microgrid configuration, operation, and control. I hope so. The people who are working in this domain here definitely have learned many things from your session, sir. It was very wonderful session, sir, and you have presented so many results, configurations, very much useful controls. Some of my students also working in this area. They have also got some good application type things. Thank you very much, sir. Thank you for joining us and accepting our request, sir. We are very much
I'm
indebted.
sorry for initial age. I'm sorry for initial age in the logging and all that. So anyhow, this
No,
they
no,
have to
sir.
wait.
No worry, sir. No worry. You have joined us. It was our pleasure. And these technical things sometimes happens, but finally you have joined, sir. It was our pleasure. And GC Bharuch is always indebted for your contributions in our FDPs. This was your
But
second
now
session.
I think the most of the people are engineers now or technologists. I think the people should come forward to now develop the product. Okay,
Yes, yes,
kind of
yes,
a
yes.
startup. I mean, they should encourage, either they should get encouraged themselves or they should encourage to the student to come up with a startup, like to convert this technology into the wealth. Okay,
Yeah,
which I
yeah.
mentioned the many things. So that
Yes, sir.
probably I will
Yes.
like to add here.
Yeah, yeah, yeah.
So,
That's why I
and
highlighted some your startups, sir, where you are working as a mentor for the successful startups. We have mentioned in the your introductory part so that some people may take
now
inspiration.
he is successful, but 1 dozen are struggling. They are coming up.
Yeah, yeah,
Every
yeah.
probably every month I am going to introduce couple of more startup
Oh,
typically.
great, sir.
Like,
It is national wealth, sir. The people of your caliber is working for the. That means this is very much affecting the GDP of our country, and we are very much thankful to you,
we
sir.
look into point of view of employment creation, like because we will say like okay, the engineers today like something like that, and probably the electrical also I can say not very topper student are coming into electrical. So we have to really show something different. Look into the only that motive behind it. Okay, we have something which really indispensable. I mean, electrical is not small. Lot of issues are there. A lot of things are in electrical. You can't run any system without electricity. Okay,
Yeah,
that's more
yeah.
important. Like,
Yes, sir.
okay,
Yes, sir.
then.
Yes. Thank you, sir. Thank you very much
So,
for joining
so,
us. Now, sir,
so can I
we will
leave?
proceed for the next session. Yeah, yeah. You can leave, sir. Thank
Okay,
you. Thank you for
okay,
joining.
okay. Thank you,
Okay, sir.
pleasure. Asutosh.
Thank you. Okay, sir. Thank you. Now, I think so. We will start our next session. Uh, that will be taken by Professor Masudan Singh, sir. I hope so. Sir has joined. I think so. Jatin, sir. Masudan, sir. Huh? Okay, okay. Just you enable Professor Masudan, sir. Okay, okay, okay. Okay, fine, fine. So, 1 minute. Sir is not seen. Okay. Uh, hello, hello, Masudan Singh, sir. Hello, 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 sir. Please turn on your camera, please. Hello. Uh, uh,
Hello.
Masudan sir का हाँ sir. Am I audible to you, sir?
Yes, yes, I am very much able to hear you. Well, what about me? Are you able to listen me?
Yeah, yeah. Your voice is clearly coming, sir. Camera is not coming.
Uh, okay.
There may be some internet issue, but anyway, we will start our session. And with your introduction, sir. Dear participants, I hope so you have enjoyed our first session uh, that was conducted by Professor Dr. Bhim Singh sir. Now in that sequence, we are going to enter in the second session, and this is also uh, going to be conducted by a distinguished guest, Professor Masudan Singh sir. Just I would like to introduce our next expert, Dr. Singh. Uh, Professor Masudan Singh sir, Professor and Registrar at Delhi Technical University. Professor Singh sir received his PhD from Delhi University. He is a member of IEEE, Institution of Engineers, Institution of Electronics and Telecommunication Engineers, New Delhi, and a life member of ISTE, New Delhi. He is presently a senior professor in the Department of Electrical Engineering, Delhi Technological University, erstwhile Delhi College of Engineering, since 2008. His area of interest includes power quality in renewable energy microgrids, control of electric machines, drives, and induction generators. Professor Singh has guided many PhD and MTech dissertations very successfully. Also, Professor Masudan Singh has authored or co-authored more than 100 research articles in various highly acclaimed international journals. Professor Singh has edited one book on electrical vehicle charging infrastructures and its challenges that is going to come very soon in the market. And I was privileged to have in his team for that book. Professor Singh sir has been serving since more than 25 years in Delhi Technological University at various capacities, including his current administrative assignment as a registrar of DTU. He is also contributing as a member and chairman of board of studies at various universities across our country. Professor Singh has developed many research laboratories in electrical department and center of excellence through funds received from sponsored projects of DST and other government of India agencies. He has also organized various IEEE conferences and seminars in the benefit of electrical fraternity at large. He had been instrumental for various initiatives and innovative activities at Delhi Technological University, New Delhi since long. Professor Masudan Singh sir, academic contribution is inspirational to all of us. With these words, I would like to invite Professor Singh to enlighten us. Thank you very much, sir, for joining us.
Thank you
and
also.
giving your valuable
I
time.
do not know, is there any issue with camera? So maybe
No
my
worries, sir.
the participants may not able to see my face. But anyway, I hope my
It's working,
voice
sir.
is
No worry.
clear. Mhm.
Yes.
ठीक
You
है,
can
so thank
share.
you
You can
those
share your slides, sir.
And since the earlier session was conducted by Professor Bhim Singh, I hope the content which I am going to talk is directly related to that only. And the topic also is of same area. So I would like to share the PPTs and then we'll go ahead. So are these PPTs are visible to everyone?
Yes, sir.
Okay, so thank you, Asutosh, again for your nice words about me. And if you allow, I can go ahead.
Yeah, sir. Sure.
So, good evening, everyone. It's a pleasure to have a discussion on energy management in microgrid, especially in this FDP, which is organized by GEC Bharuch under the leadership of Dr. Asutosh. Uh, I am thankful to Asutosh for giving me this opportunity and also his other team members who are organizing this event. So let us continue what you had in the previous session. Uh, I could see few of the slides of Professor Veem Singh. He also talked about microgrid. Uh, I will have initial talk related to few basic definitions of uh, microgrid, and then we will move accordingly. Uh, as Professor Asutosh already pointed out, I come from Delhi Technological University, a professor of electrical engineering there. And if you see this very first slide, microgrid layout is shown, where you see different kind of energy resources, like we have a wind generation, you have uh, battery storage systems, and you have different kind of local loads. Before we go into microgrid, I hope most of you are aware about the definition of a conventional grid and a related term like smart grid, nano grid, etc. Just for information of audience, uh, what is a grid? I hope people from electrical engineering know this term. When we refer grid means a very large scale power system, and conventionally such large power system has three major components. You all know it has a generation, it has generation, transmission, and distributions. So this is your conventional grid, and the target is to ensure a reliable delivery of electrical energy. So at the in the power plant, we generate through transmission line, we send to the desired destinations, and in distribution network, the electricity is utilized. This is what is our normal grid. Now, I hope you are aware with this term also, smart grid. What makes a normal grid a smart grid? So, if you look to the definitions, uh, in a normal grid, if you try to incorporate information technology networks, communication network, and also automation technology, this makes your normal grid a smart grid. So with this provision of information technology, the load and generations are able to communicate with each other. So that smartness or that provision makes your normal grid to act as a smart grid. So all modern grids are now slowly converting to a smart grid. And there is a similar word I hope you have come across, nanogrid. A single building, a very small scale power system whose capacity uh, is of order of nano with respect to normal grid. Usually we refer as a nano grid. Here you may have small energy storage devices uh, connected together to meet a small scale power system requirement. So this is just for uh, your information that how we distinguish a grid, a smart grid, a nano grid, and finally coming to microgrid. So the word microgrid, I hope, might have been deliberated in the previous session also. This stage, if you see this definition, microgrid, basically a group of interconnected load and distributed energy resources. Now this DES, what we usually call distributed energy resources or sometimes distributed generations, mostly refer to renewable energy resources. So if we have a arrangement which can uh, meet our local demands, especially in the region where the normal grid is difficult to let down, or if the normal grid is unable to reach places like hilly regions or remote area where you have maybe some military bases or maybe some critical loads like TV towers or mobile towers, you may have an arrangement like microgrid to meet the power requirement there. So it's just you can think of microgrid is a small grid meant for meeting the requirement of a community. That community may be a military base, could be a hospital, or sometimes even a university, you see, uh, has a lot of solar installation and other energy resources. That also may be considered as a microgrid, because as and when you have a possibility of grid supply available, you operate your microgrid in grid connected mode. And in case if there is a power failure, you have some critical load, you may isolate your microgrid from the main grid. And this is how you can not only improve the reliability of power supply, but also you can have a effective utilization of energy resources, and you add resilient in the grid system. So that is what is the thought behind microgrid. Uh, I think these are the few obvious observations about microgrid. Why microgrid power generation? So the reasons are quite clear. If you see, one of the main reasons is that we want to feed remote locations where it is difficult to maintain a normal grid supply. Say, for example, if it is a very remote hilly area, maybe during winter there is a chance of snowfall and all. It is very difficult to maintain the normal grid supply. In those cases, if you have some local generation system which can be operated in an isolated mode, can help to feed such locations. EG control and operations is another region. Third, if you see, for increasing the renewable energy share. So day by day, hope you all know the government is encouraging to go for more renewable. I hope majority of you might be aware that our current installation of our current installed power requirement is around 450 gigawatt, and out of that around 30% is the contribution of 33-34% is the contribution of renewable. So renewable share is increasing day by day. And among renewable, if you see, the major player is solar. So out of 34 or 35% total, if you see the contribution of solar, around 60%. So broadly, you can see that among these renewable, the solar and winds are coming in big way. And other issues related to power generation is in microgrid is that since you can operate it in a isolated mode as well, uh, you don't need any regulatory body for that local operations. The arrangement could be a less expensive. If you are operating in isolated mode, you don't have transmission line and transmission equipments, and also that makes your system less costly. And for reducing the burden on the grid, that's another issue, that if we go for microgrid, local generation, that indirectly reduces the burden on the grid. For reducing the greenhouse emission, this is another challenge the whole world, I hope you know, is facing, the environmental pollution and greenhouse emissions, especially due to thermal power generation. So day by day, the efforts are to reduce the coal-based generation and add the renewable-based generations which are more eco-friendly. Increasing the overall economy is another interesting fact about microgrid. Apart from that, you see the increase the energy efficiency due to closeness of load. Since load and source are locally managed, you have an efficient system. The losses are less in the systems. So that way microgrid is considered to be more efficient system than a normal grid. Peak load reduction. So as you have seen earlier also in your previous session, that every microgrid has scope for energy storage through battery energy storage system and all. So that helps in reduction of peak load, enabling the grid modernization. This is another aspect. You see, our conventional grid is getting modernized because once we integrate renewable energy, there are many things which were available in conventional grid we need to modify. For example, the normal load flow analysis you do for a conventional grid need special modifications when you add the renewable energy sources. Not only that, if you look to the protections, conventional grid usually power flow was mostly from generation to load. So accordingly the protection systems were laid down. But here there is a intermediate resources integrated different places. So the protection also need to be modified if it is a microgrid. Encouraging third-party investors, another aspect, local control for maintaining power quality and reliability. So if it operates in isolated mode, you can maintain the voltage frequency locally with the help of power electronic systems. Promotion of community involvement. This is another interest which is encouraging the involvement of local people, not as a consumer of power, but also as a power generators. So if they have a surplus energy, they can either store and utilize when the grid is available, feed the grid. So these are the few important aspects of microgrid. Apart from that, why we should go for microgrid region appears to be obvious. We want to use natural energy resources which are in abundance, especially solar, wind, electric grid supply is either costly or not available. This was the reason which I told you. Many remote places, grid supply is not available, and there microgrid appears to be a very interesting and viable options. Moving vehicles and train ships, the energy could be utilized. Need of local generating units for critical loads such as a hospital, etc. So when you especially uh, find a situation where normal grid is not available, you operate your microgrid in isolation mode, islanded mode, and there you categorize the local loads, few as a critical, few non-critical. So the loads which are important need 24-hour supply like hospitals, ICU unit, etc. They could be placed in microgrid, uh, on microgrid, especially in isolated mode. So these are few interesting facts about microgrid. Now, what exactly a microgrid consists of? If you look, it consists of uh, all possible kind of energy sources, mainly renewable sources like wind. You have solar. Apart from that, if there is a possibility, you may add biomass, tidal and ocean power also. So broadly, if you see, renewable mainly contributed by solar and wind. So one thing is that you need resources, and the second thing is you need mechanisms, you need machines which convert these natural resources into energy, especially electrical energy. So you need generators. So if you are using wind, obviously you need wind energy conversion systems to get electricity. Similarly, solar, you need power electronic systems to convert solar energy, which is basically from solar panels, the DC energy to AC energy, because most of your equipments operate on AC. So you need converters technology. So we need resources, we need conversion systems, maybe a electromechanical conversion system, that is a machine, or it could be normal power electronics converter to interface these energy to the loads. Load could be of any variety, linear, non-linear. Power electronics converter, as I said, and in microgrid, to enhance the inertia of the systems, we do need battery energy storage systems, auxiliary loading system, etc. So battery energy storage, supercapacitor storage, that all helps for storing energy, releasing energy, and directly enhancing the stability of the grid. So these are the few uh, major components of microgrid. Now, what exactly on the challenge in the microgrid operation? Uh, the first, if you can see, one of the major challenges selection of site. What are the resources available? Because you see that if it is a hilly area, usually uh, it is the solar energy availability high. If it is a seashore, you see wind energy availability is high. So accordingly, you select the systems which will convert those resources into energy. Selection of generation resources. Uh, so if it is both availability, you see that what mix operation you can think for a better utilization of these resources. Now, in my talk, I would like to focus more on this aspect, that is, in microgrid, we have generation which is based on wind energy. So, what we usually refer as wind energy conversion system, and if it is a microgrid, you know that the sources which are integrated in microgrid are usually of smaller capacity of order of few kilowatt. So the kind of generators, if it is a wind energy based generation, uh, what are the various type of generation schemes, we will talk a little more details. And once you operate this microgrid in isolated mode especially, there is a major bottleneck how to maintain voltage and frequency, because it's a small grid. In your main grid, conventional grid, maintaining frequency is not an issue. The grid inertia is so high that frequency is maintained automatically. Here you see you have small sources and they are connected together in a predefined boundaries. So at the level of boundary, they all together work as a single entity. So maintaining the voltage and frequency, especially when they are operating in off-grid mode, is a issue, and how it is addressed. We will talk about these issue in details. Continuity and reliability is another challenge. Regular maintenance, because especially microgrid, one of the major issues is safety and regulations. If you operate a few resources locally, there is no company or there is no normal grid supply to maintain that, and therefore the regulation is an issue, that who will regulate those systems, who will maintain the standards. These are the issues which mostly microgrids are facing, because if you have your own machines operating locally, maintaining their power quality, stability, standards is your local issue, and those need to be addressed either by the investors, operators, and users. So this safety and regulation is a major concern in microgrids. Well, coming to the next slide, if you see, it's a architecture of a microgrid, where we have considered four variety of sources, like a wind turbine, you have a battery energy storage system, solar cell, and fuel cell. And we have a common bus here. You see, through required power electronics interface, we connect all these resources to a common point of coupling. We usually refer PCC, and we categorize the loads either as a critical load or non-critical loads. And especially when you operate in a islanded mode, I mean when you open this switch, this isolator, you ensure that supply to these critical loads are managed by these local resources, and these sources of energies are maintained in such a way that the voltage and frequency of this network remains in the prescribed limit. So that is what is the priority of this grid, that even your normal grid is not available, you can meet the requirement of this high demanding load. Like this critical load could be a hospital load, could be a military base, or could be any other similar important load. Non-critical load, obviously, when you are operating in grid connected mode, you can feed those. So this is just a general structure of a microgrid. But by and large, when the term microgrid was coined, it was understood that all these resources which will be connected to this system will not be of a large capacity. They may be of the order of few hundred kilowatt. So accordingly, the terminology grid coined because microgrid was coined, because you know that this normal grid capacity is gigawatt. If individual source, here you see kilowatt. So this kilowatt divided by gigawatt, if you see, that factor comes order of 10 to the power minus 6. And that is the idea to say that this could be treated as microgrid, right? So the rating of these machines for micro order with respect to normal grid. Well, this is just a general layout of microgrid. The mode of operation, I hope many of you might be aware. Grid connected mode is the most common mode. Whenever grid is available, we operate it in a grid connected mode. If grid not available, you can switch to standalone mode and battery charging mode also. Because if the standalone mode, the critical load is not adequate to maintain the voltage frequency, you can use battery charging mode. So you can store some energy during that period, and the same could be delivered to the grid when you operate in the grid connected mode. Now, grid connected mode, what are the expectations? In grid connected mode, you see that the converter connects the power source in parallel with other sources and to supply the local loads. Possibly it feed power into main grid. So when you call grid connected mode, we see that all the local resources, wind, solar, biomass or fuel cell, they are just like operating in parallel through their respective power electronics converters. And parallel connection of these embedded generators is governed in the same way as our generators in normal grid operates with those standards. Power injected into grid can be controlled either by direct control of current fed into the grid or by controlling the power angle. So I hope this you might be aware that when you have a machine, synchronous machine feeding normal grid, you use power angle, that angle delta, to control the real and reactive power share with the grid. And if you have resources which are connected to the grid through power electronic systems, it is the power is injected into the grid through usually current control mechanisms. So most of the converters through VSC, we try to control in current control mode to operate, to inject power into grid. In later case, you see that voltage is controlled, that when you talk about delta control or power angle control, and we consider that voltage is sinusoidal. But you know that if it is a wind or solar system connected to grid through a converter, this voltage may not be a sinusoidal voltage. So for power angle control, uh, without directly controlling your output current, uh, it is not possible unless and until your profile of voltage is sine. And that's why if it is other than sine, the THD should current come into picture. What you call when the grid voltage is distorted, right? So, and another interesting fact about the grid connected mode is the electric machine generators, which effectively used for converting maybe wind energy to wind energy into electricity. For machine, we find power angle control relatively easier and more effective. Another fact is that converter output current or voltage, if you are interfacing any solar or wind or maybe fuel cell to the microgrid, synchronization is a major requirement, I hope. You have to ensure how the grid supply is synchronized with the supply which is generated by the DGs, or what you are calling distributed generations. And phase lock loop is one mechanism which helps you to synchronize these systems. Grid voltage zero crossing detection is another mechanism what you call to ensure the same. Now, standalone mode is another option that when grid is not available, we operate the local grid, we are calling microgrid, and the requirement is that when you are operating in a standalone grid, your requirement is to feed critical loads, and in this islanded mode of operation, maintaining voltage and frequency is a major issue, and for that we need these two methods. If you are aware, one is called frequency and voltage droop method. Now, this method, if you think of, is more or less similar to the frequency control in normal grid. When you have more than two generators operating in parallel, how do we manage frequency and voltage when you connect them to the grid, especially droop control, which you utilize for sharing power. So you have number of generators operating in parallel. Which generator will contribute how much is decided by the droop curve, which is characterizing that particular generator. Other option is master-slave method, where one of the converter acts as a master, setting the frequency and voltage and communicating to the other converter for the sharing of the load. So this is another mechanism, but you see broadly these are the two ways when you operate microgrid in islanded mode, either with the droop method we adopt to regulate voltage and frequency, or this master-slave arrangement. Now, third option, as I said, was battery charging. What exactly is battery charging mode? In microgrid, you have storage batteries and other energy storage devices. And these devices are needed to handle the disturbance and fast changing loads. So if you have energy storage systems, these energy storage mostly BES, what you call battery energy storage, or sometimes supercapacitor also. So these energy storage is needed to accommodate the variations of available power generation and demand. Because it's a local grid, if you increase the demand and the generations has a limited capacity, then the difference, if there, need to be managed through some alternate arrangement. Battery storage helps in meeting those demands. The power electronics converters could be then used to charge these batteries. So if there is a excess of generation, obviously you can use those excess energy to feed the battery and utilize the same when the load demand is more. So battery charging, discharging, just for either storing energy or releasing the energy. Now to see how do we connect uh, the these local resources to grid, you need mostly power electronics converters, right? So hope you are aware of this converter topology. This is the three-phase converter. You can call three-phase VSC, voltage source converter, which can be used for two-label conversion. So though we have variety of converters control to ensure two-label, three-label, or multi-label converters, depending on their requirements and complexity of the systems. Broadly, if you see, it is the two label and three labels which are used in practice because their control is simple and operation is also simple. So this is the two label. You have plus VDC by 2 and minus VDC by 2 terminal, and these are the three-phase AC side. We control these switches in such a manner that the output is an AC output. So if you look to the operation of a two-label inverter or two-label converter, these are the switching functions for each leg. So this is the one leg, you see the upper switch, the lower switch. So there are two possibilities that if we adopt this switching state that this upper switch is on, you see the current can flow to the load, and then it is greater or equal to 0. The voltage at the load is simply VDC by 2. And there is a possibility, because this is a IGBT with default diode across it. So this diode is enabled to operate to inject the current to the grid when the current is less than 0. That it provides a path for reverse current. So if the upper switch is on, there are two possibilities to allow the current, either current to the load or current from the load. Similarly, if you see, the other possibility is that when the lower switch is on, when the lower switch is on, you see the current the negative current can be allowed to flow like this, or in other option, you see that for current greater than 0, we take the help of this diode to make the path for current. That way, you ensure at this terminal the negative supply reaches and it is minus VDC by 2. So this is just the basic of a two-label inverter. What are the switching functions which you ensure for implementation of PWM control and ensuring an output which vary either at plus VDC by 2 or minus VDC by 2. Now this is another topology of three-phase converter. Hope you may be aware. NPC converter. So neutral point clamped converter topology. You see, one leg of this NPC consists of 4 switches in series and 2 diodes. The other 2 legs are similar arrangement. So with these diodes are called clamping diodes, and with this arrangement we ensure that each switch has only half of the voltage during its off states. So there are 4 switches, and if you see the possible combination they can be switched on is 2 to the power 4, right? However, when we are interested to operate it as a multi-label, say for example, commonly used as a 3-label inverters, you have a switch that is 1 and 3 and operate together, 2 and 4 operate together. So we have 2 pairs, and the switching function we will see now. How do we ensure that this converter operate as a 3-label inverter or 3-label converter. So this is the switching scheme for, you see, the switching function for a leg of NPC. We have 4 switches, you see. So if you make the gate of the switch 1 and 2 high, that is 1, you see the path for current is such that your output voltage is plus VDC by 2, and since the both has anti-parallel diode, you can feed the current from load to source via these diodes. So that is the state when the current is negative but the voltage is still positive. So whether it is feeding the load or it is feeding the grid, in both cases you see the output voltage is VDC by 2. So this is called neutral clamped NPC, neutral point clamped converter topology. Similarly, if you operate the other 2 diodes, other 2 switches 3 and 4, they are high, the current can go to the load like this, the voltage will be negative, and other possibility is that when the load is feeding the current, the still voltage is negative. And the third option, because of which we are telling it is a 3-label, the 2-label first is this, second is this, third label is the neutral voltage, VNP. So under that condition, you see the 2 is high and 3 is also high. So under this situation, you see the neutral voltage appears at the output. So this way you say that on this topology, we have discussed one leg. Similarly, the switching functions for other 2 legs can be developed, and these 3 legs together can give the effect of a 3-phase converters for 3-phase systems. So this is a very common topology for multi-label converters. The earlier one we thought only 2 labels, and broadly, as I said, most of the practice you will still find these two level, 3 level very common. Though we have higher levels converters, they have their own advantage, for example, of the profile of voltage and quality of output waveforms, have less harmonics and all, but their control is accordingly complex. Another possibility is this CHB, what we call cascaded half bridge topology. So you have a single phase half bridge, single phase bridge you see, and this output of these all three single phase half bridge are connected together. So this topology is also used in some of the converters, and it has its own advantage. Maybe requires less number of sometimes switches and also a better operation. These are the standard switching states of different combinations. You see here how it ensures the 3 level, either VDC by 2 or minus VDC by 2 or 0 level, and accordingly the switching functions for a pair of switches shown here. Say the switch 1 and 4 if operate together, you ensure a voltage VDC by 2 and a positive current. And with these anti-parallel diodes, you can ensure a negative current but a still positive voltage. So similar arrangement for 0 volt, this arrangement, and minus VDC for other pair, that is 2 and 3. So you see either VDC by 2 or plus VDC by 2 or minus VDC by 2 by operating 2 switches of in pair, one from upper side and other from lower side. Whereas for 0 voltage, you have to operate a pair of switches from same either upper side or the lower side. So this is the one configuration which is also used for with some of the energy resources for converting these local energy into grid. These are the few simulation circuits that we may take up later, but let me tell you few configuration of wind energy generation systems. I hope this is one popular single phase wind energy based generation system where you see you have wind turbine coupled with a induction generator. We call it a SCIG, and people of electrical engineering may be aware SCIG stand for self-excited induction generator. So basically a single phase induction machine or a single phase induction motor where I hope you all know every single phase induction motor has 2 winding. One is auxiliary winding and other is main winding. So in such a machines, if you connect a capacitor in auxiliary of an appropriate value, depending on the wind speed here, the main winding has capability to generate voltage. And that is what is the principle of this SCIG. That an induction machine, when driven by a prime mover and a capacitor is connected in auxiliary of appropriate value, the machine start generating voltage, and that is the case of, you say, it is a induction generators. Now this arrangement could be extended even for a three-phase induction machines, where in spite of having a single capacitor, you need to connect a three-phase capacitor bank. And since in three-phase squirrel cage machine, the only stator which you can access, this capacitor bank is connected at stator only, as the rotor is a squirrel cage in three-phase machines. But if it is a single-phase generation, then this main winding voltage we can feed to the load. For example, the load is here a combination of linear load, inductive load, as well as a non-linear load, which is a rectifier feeding some DC load. And to maintain the voltage at the point of common coupling, we take the help of this full bridge, single phase full bridge, as a VSC, where we have 4 switches, S1, S2, S3, and its DC side, you see, has a energy source, maybe battery, which can act as a battery energy storage system for this. So if the load demand is high and generator is not able to meet, the same could be made through this battery. And in other case, when the load demand is less, you have excess energy can be utilized to charge this battery. So for ensuring discharging of battery, discharging, we have a switch at DC link, which ensures the charging and discharging of this battery, and also maintaining the DC link voltage if it is required to be maintained, right? So this is a mechanism for single phase power generation through wind turbine. And for a typical requirement of loads, we can design this system. You can think what would be the capacity of the wind generator if the wind speed availability is known, and accordingly what would be the size of this inverter, how much battery bank we need, and so on. So my next slide is on three phase, what I talked about. If you replace that single phase induction machine by a three phase squirrel cage machine, then with a three phase capacitor bank on the stator of appropriate value, this stator has capability to generate voltage and feed the load. So here also you have a non-linear, 3 single phase nonlinear loads are demonstrated, so that if this generator face a worst case loading of 3 phase load, maybe with single phasing and all, how we are able to maintain voltage at PCC and also the frequency, and we ensure the quality of power supply here at the load terminal. So you are having a 3-phase VSC here with a battery energy storage, a DC link, and a interface inductor which is required to connect this VSC to the PCC. So the value of this interfacing inductor is also important when you connect any VSC at the PCC. So this is a wind-based DG system, distributed generation system, which I talked initially, a single phase generation. And in the limited time, let us have a quick look. In this system, if we have to design this entire system, depending on the availability of wind resources, how do we decide the value of capacitors? How do we decide the rating of this single phase inverter? How much is the value of these filter inductors or interface inductors, and battery bank capacity, etc. So if we have to design such system, the first step is to decide the rating of your turbine. So that is what is called turbine design, followed by selecting the rating of generator, that is this single phase induction machine, and then how to decide the rating of these interfacing inductors, and finally overall rating of the VSC, kVA rating of VSC. If you have used a transformer, how to use the how to decide the rating of the transformer, and battery backup requirement, that is here on the DC side. So these six designs will make you to make a complete single phase wind-based energy conversion systems which utilize an induction machine. And you'll see that induction machines are low-cost machines and relatively easy to maintain, and that is the main reason to use such machines for wind energy applications. Further, they are more suitable for variable speed generations. That's another interesting fact about this if you compare with other variety of generators like permanent magnet and all. So how to decide the design of turbine? So selection of the wind turbine rating is important, because it works as a prime mover for your generators. So for a wind turbine, if you see how much mechanical power which need to be converted, that all depends on the velocity of wind available there, the sweeping area of the turbine plates, the air density, and the CP, which is called the TP speed ratio. And this CP is called power coefficient, which decides the net mechanical power which you can generate through a wind turbine. So this is a very conventional equation which most of you may be aware, that the mechanical power available from the wind turbine is proportional to cubic of the wind velocity. This wind velocity is in meter per second, and this is a power coefficient we call CP, which depends on basically two factors. One is called TP speed ratio lambda, and the blade pitch angle that we call beta. So how this lambda and betas are defined: lambda is this blade radius, the turbine blade radius, and this the wind velocity decides what is delta, what is this lambda. Power rating of single phase generator. Say if we consider that the machine we are using, we are having is a 3 HP induction motor, which comes around 2.2 kilowatt, and its efficiency is about 85%. So if this is standard rating you select, then mechanical power input for this generator, I mean to generate this much watt, 2.2 kilowatt from this generator with this efficiency, you need mechanical input, that is this factor divided by 0.85, which comes 2600 watt, around 2600 watt. So this is the mechanical input which the generator requires at the turbine end. But between the turbine and generators, we also use gearbox. So gearbox has also some efficiency issue. So if we consider the loss in the gear maybe around 10%, then additional watt which need to be generated by the turbine is 10% of the generated power, the mechanical input. So this comes around 3000 watt or 3 kilowatt. So we understand that with given motor ratings and its efficiency, we can decide that how much power, mechanical power we are expecting from the turbine. And with that much mechanical power to be generated, we decide what would be the turbine radius of the turbine blade and other factors depending on the wind speed available. So if you consider that the wind speed has this range, say maximum 12 meter per second, and the other factors of lambda, beta in this range, we can find the value of the radius is 1.4 meters, right? This 1.4 meters you can find using this formula which I told you earlier, right? So this is how we decide the size of the blade for wind turbine, and followed by how do we select the size of interfacing inductor. So that requires how much, because this inductor has a role of smoothing the current. We specify how much current variation you can tolerate at DC link, that ripple current you can allow in the AC side, we call I peak to peak, and you have a DC voltage, DC side, you have modulating frequency FM for converter. So this is a standard formula which correlates the interfacing inductors with DC link voltage. This I peak, we have to decide how much current ripple we can allow, and these are the frequency, and this safety factor K is all specified. So usually if you are operating at a frequency, modulating frequency around 5 kilohertz, safety factor you are considering 30%, so 1.3 K. And we allow this peak to peak ripple around 10% of what is the output current of VSC. So at the given DC link voltage, this modulation index worst case value X, you can consider 1. So with this values, you can find out how much will be this LF. So again, to find the how much reactive and active power this VSC has to consume or supply, accordingly we can decide the power rating and current rating of the VSC. So this is how you can decide the rating of all these components. I think these formulas are standards, and with this you can find the voltage at the DC link, because to ensure PWM control of the inverters, you need the battery side voltage higher than the peak of your AC side. So accordingly, this DC link voltage is also decided. which in this case comes around 396, which we have selected around 420 volt. So this is the battery voltage at the DC link, and accordingly you can decide what would be the kilowatt hour capacity of your battery bank. So this way, using these standard calculations, you can find the rating of the battery, that is the ampere hour rating. You can find the inductor interfacing inductor value. You can find the kVA rating of your inverter and so on. So I think uh, uh, today we can restrict it here, because these are few basic discussions, and since we have opportunity to go little more details in this converter topology, we can continue tomorrow if required. So Asutosh, are you available?
Yes, sir. Yes, sir.
So what about your timing? Is it okay, or should I go
Yeah, sir.
ahead?
Actually, we are running short of time. Your session is almost completed, sir. Up to 9:30 it was planned, and session delivery was very much wonderful, sir. I hope so. Things you have discussed in very much in detail and very clear manner, sir. And I was fortunate enough to attend this session and learn something from your session, sir. And there are few questions. Can we take, sir, today?
No, I have no issue. If you have time, I can obviously comment on that.
Otherwise, question hour can be keep tomorrow if you wish.
Yes, yes. No, because our some of the portion is still left.
Yes,
It
yes,
would be
yes.
better if we
Because
continue.
I hope so the questions put up by the participants will get automatic answer from your remaining session.
Maybe
Because
because I do not
I
know.
understand I understand the questions.
Uh,
It may come in your future slides, sir.
hmm. So I think now next slides are mainly related to three-phase systems.
Yeah.
So that we will take up tomorrow.
Yeah.
And if there are one or two quick question, we can go. Otherwise, if you,
Yeah.
you
Actually, just I am taking one or two questions today, sir.
hmm,
If you
if,
allow.
yes, yes, fine.
In case of battery energy system, Dr. Hemang Pandya is asking, in case of battery energy system, which are the effective strategy for stable performance throughout the load delivery in both charging and discharging cycles? That means he wants to ask the role of battery to stabilize the active power flow during charging and discharging.
If it is a microgrid operation in islanded mode,
Yeah, he is asking about microgrid operation only
uh,
in islanded mode.
so obviously, I hope this question was raised before Professor Veem Singh also. Similar question, I hope, where he said that it is the battery energy storage, sometimes in combination with supercapacitor, which helps adequate inertia to the grid, especially in storing energy, supplying energy as per the demand, and that enhance the stability of the grid, microgrid especially. So a microgrid which has adequate size of battery storage is obviously a better and more stable grid, a stable microgrid, because it has adequate inertia. And fortunately, if it has a wind energy based generation, then these machines also add good inertia to the system as far as the stability is concerned. But yes, if it is mainly solar based microgrid, obviously you have battery energy and supercapacitor combinations that could be of adequate size. Right. So hope I answer the questions.
Yeah. Yes, sir. Yes, sir. And there is one question, I think so, that is related to power system protection.
Mhm.
Mr. Ravindra Kisan Rao Mankar is asking, adding DGs into existing system, problem of relay coordination in protection system occurs. How to
Obvious.
resolve that problem?
Oh no, I said I hope in the beginning might have he was carefully listening that in conventional grid you have unidirectional power flow from generation to load. So bidirectional relays are usually not of that importance. But in such system where you have integrated DGs, you have a power flow in both way. So obviously the protection system need to be modified and hope in most of the systems, DG systems, most of the grid systems which are integrated with DGs, you have a new, you have a different protection schemes. It is not your conventional which works as it is. It need to be modified.
Yes, sir. And we will take only one more question and then we will wind up the session. Uh, Mr. Mrityunjay Mani Tripathi is asking, how is a PV DStatCom different from a grid connected solar based microgrid? That means he is asking about the role of DStatCom in solar based microgrid.
Or
I
these
think
that
so. It is the,
and
yeah,
VSC more or less same thing. The only thing is that when these StatCom you say it was used mostly in power quality sense, where you have to ensure power quality parameters like real power, reactive power, and uh, mainly harmonic and other issues. But when we use this, especially for along with renewable energy, the same converter topology with a little different control. The main focus is to transfer energy from
yeah,
your renewable energy to the grid or to the load. So when the StatCom word used initially more on power quality related issues. Later on, it has become now a very common word VSC, which is very versatile.
yeah, yeah. And one more question, but I think so. It is very clearly answered in your one of the slide. How to select optimal location of DG into system?
Oh, that's all a power system area
Yeah,
where,
yeah. People
yes,
may have working in the power
that,
system
yes.
optimization.
I think some of my students also worked how
Yes, yes,
to place a DG depending on the performance index of your distribution system. So there you need multi-level, multi-objective programming. Uh,
yeah.
so power system people, I hope they know it, how to, uh, what are the criterias they have to ensure and to meet those criteria, how to optimize the performance of the distribution network. So that itself is a interesting area in itself.
Yeah.
Less power electronics there, but more on focus on power system analysis.
Yes, sir. And another queries will be taken later tomorrow. And thank you for joining, sir, and delivering so late, sir. I can understand your busy schedule, and you have given us a very much valuable time from your busy schedule. And I hope
It's
all the participants have enjoyed your session and learned something in their research. And I hope so. Your next session, which is going to be at 6 p.m. tomorrow. That is also going to be enjoyable to all the participants. And from these words, I would like to sum up the session, sir. And thank you very much for joining us, sir. And thank you very much. And we will again meet at 6 p.m. With the same expert. Thank you very much, sir.
Thank you, Astos, and thank you all participants for your patience hearing. Wish to see you all tomorrow. Thank you.
Thank you, sir. Thank you very much. Now, all participants, you can leave the session and you can enjoy your dinner. Some of you may have already enjoyed your dinner, but the rest can enjoy. Thank you. Divyesh,
Hi, sir.
hello.
Yes, sir.
Attendance,
Hi, yes, sir.
attendance as per planning you have downloaded. Na?
Yes, sir. Yes, sir.
Okay, thank you. Fine,
Okay, sir.
fine. You keep in your record
Yes.
session-wise attendance. We will
Okay.
discuss. Okay.
Okay, sir.
Yeah, all the organizing team members, now you can leave. And again, we will meet 15-20 minutes before the scheduled session.
Okay, sir.
Thank you. Thank you, Jatin sir. Thank you, Professor PK sir. Thank you very much, all participants, for making the sessions very much interactive. You have asked many questions. I hope so. People have answered. Experts have answered questions very satisfactorily. And now you can enjoy your food. Thank you.